So the next concept we're going to consider in our physics course is the concept of energy. Now this is an interesting topic, and it's also a tricky one for students because it is an abstract topic. Now listen, so in our general world we have a general awareness of what we mean by energy. Okay? So if we're out of it, we're tired, the car out of gas, etc. Such things like that. We understand. You know, let's go play tennis. Oh, I'm tired, or whatever. And we understand that we're lacking energy. But that doesn't really help us very much in the scientific world. So from a scientific standpoint, what we want to be able to do here is to quantify, because this allows us to make predictions. Now let's go back up to the previous situation. The car is out of gas. We want to drive from here to Grandma's house. How much gas do we need? Well, there's a calculation, because it'll be the amount of energy the car needs to get to Grandma's house, and then how much energy is per liter of gasoline and all that. So, but this then allows us to quantify. Now we can begin to say, okay, how much gas do we require? And there, how much does this gas cost? Therefore, we know how much it costs us to go to Grandma's house. So there's an important factor there. What we're also going to find is that we found first we had motion, which was then caused by forces. And what we're going to see now here is that energy, at least in the mechanical sense, will create forces. However, before we get any further down the road, we should maybe decide what the definition of energy is. And this is where I think we have misconceptions. Now, perhaps I'm unsuccessful, but I believe that one of the problems that students face in physics education is that we're taught things a certain way in high school and perhaps at the beginning of university, and ultimately when we get to more sophisticated worlds, we kind of have to relearn things. I don't think that is very fair. Now, I understand things get more complicated and all the rest of it, but I think we should be very cautious about the simplifications that we make. Now, let's look at this one. The typical one that you will see in almost everywhere is something like this. Energy is the ability to do work. And it's very commonly used. So here's some problems, just as an example with this, and why I'm not comfortable with this definition. So first, let's see what work is. Well, this is defined as the exchange of energy in a process. So it is clear right off the bat we're in trouble, because if work is energy, then how can work be used to define energy? That's sort of like energy is equal to energy or something, and that's just not adequate. Furthermore, work is mechanical. Energy is a far broader concept. So if you take, let's just rub this left side off here. If you look at, for example, different kinds of energy, we could have chemical energy. And of course the chemists, they love doing experiments, so we could have a change of color. We could have a change of temperature. And things like that. We have nuclear energy. Or we can have a change of substance even, right? And so forth. And you of course have a host of other energies, electrical and sound energy, and on it goes. So to me, this mechanical definition of energy is simplistic, it is limiting, and inarguably is incorrect given the definition of work. So I think we need to try a little harder here. So let's do that. So my version, which is what you'll use in this course at least, and then you can see after that. So energy the ability of an object to alter its circumstances. I've seen others say its form. So we can look at it wherever we want to here, but this is close enough. Now the ability here is not a personification. A piece of chalk that is dropped does not make a decision to fall, but it has the ability to fall. And this ability can be quantified. So a heavier object falling does more damage. And so we can quantify what's happening here because we can determine the mass of the object, for example, and the gravity field or whatever else we're doing. And so we can recognize in the same way that an object moving more rapidly were to strike something, there's a greater effect than if it's not moving as fast. So there is ways to quantify it. And I'll restate the concept of work is the energy exchanged in a given process. Now, we have to be careful, as I've said many times in my instruction, about metaphors, but I think this one at least can start off with, is that energy as a concept is similar to money. So let's look at the concept of work. So we want to buy a chocolate bar, buy a candy bar, and say this bar costs us $2. Our net worth is irrelevant. The storekeeper, the store clerk, needs only $2. This can be your own, it can be borrowed, and they won't know and don't care. Now let's look at this as a money and a energy concept. We want to buy a candy bar. This is the exchange of energy. We want something to happen, and the amount of energy required, the work done, will be represented by the $2. So it doesn't matter how much total energy is available. So for example, if we drop a penny from a meter onto the floor and it creates there's a certain amount of energy released by gravity doing so. Or we drop an automobile. Okay, all we're looking at is the amount of energy that's exchanged as that action occurs. So the repository of Earth and its ability to produce energy is enormous for us small humans. But it's not important when we don't care when the penny falls to the floor. It's irrelevant. It's not going to damage the foundation of our home, for example. So if you have to think about energy and work, use a money analogy. And it's very true in our society too. Buildings don't get built, processes don't get happening, projects don't occur, people don't get hired, and their services therefore are denied if there's no money made available for those services. And so money really, in our economic world, is the energy, if you will, that allows things to happen. Now we are, as humans, far more familiar generally with basics of money. And so this can help you appreciate it. But let's go back here before we rub things out. Energy, the ability of an object to alter its circumstances. That will cover everything that we talk about, not just mechanical physics, but all types of physics. And work, the energy exchanged in a given process. Okay, so these things matter. And then we have this metaphor here with energy and work. So let's try and get a better feeling of what we've got here. So we're going to do a simple thinking experiment. We'll have a mass, m, and this is one experiment, but we're going to analyze it in two different ways. We have our ground down here somewhere, and the object is dropped. Okay, so there's no fancy stuff. It's a simple dropping. The object will travel in this way. It is acting under the force of gravitation, and for the purposes of this, that is a constant force. It doesn't have to be, but for now it is constant. And this is true in this one as well. Okay, it's exactly the same experiment. In this case, we will recognize that the force acts over a particular displacement. That the force is acting over the entire time the object falls, not time, pardon, but over the entire displacement that the object falls. Over here, instead, we will look at it under time. So in this case, we have force times displacement, and here we have force times time. So same experiment. Okay? We're just looking at the data separately. Now, we have to be careful about just analyzing units and hoping for the best, because we can fool ourselves that way. So initially, at least, we're going to talk about it and just define it, so to speak, and then we'll go back maybe later and look at it more. When we multiply the force times the displacement upon which it acts, we have what is known as energy. In specifics, this is really the work done by this force, but that will come later. But that's an energy argument. Over here, we have momentum. In fact, what you're seeing here really is a change in momentum, which is an impulse. But that's another day. Now we're going to, in grade 11 top physics, we'll talk a little bit about momentum, get a bit of a feel of what it tells us and what it doesn't tell us, how it helps us in certain situations. But we're going to spend a lot more time with energy and work and so on, as it's so important. Now remember, people, these concepts become abstract, especially in the case of energy. And it takes time to understand it. Problems related to these can be obscure and take time to figure out. And the primary reason overall is that you have to know the definitions of these words. And you have to not only be able to regurgitate these definitions, you have to understand what they mean. And there is no gimmick. We can talk about the general sense of what these things mean, of course, but what we cannot do is just wave our hands and immediately get a feel for it, because you don't have a feel for it. This is work, pun intended. And we need to spend time with it and really begin to get a feeling of what they are. And then when you do a problem, you'll find constraint theory really helps you, because when you use constraint theory, you say, okay, what is the fundamental constraint here? And often the case will be there's an energy argument, that the energy going in is equal to the energy coming out. Okay, well, what is the definition of the energy going in and out, and so on? And you'll find that if you can do those things, then you understand it. And if you're stuck, well, then you need to go back and remind yourself what would be the technical definition of the energy coming into a particular circumstance, and so on. Momentum was characterized by Newton as he called it, a motion effect. And it is another phrase that we understand in an intrinsic way. You're riding your bicycle down a hill, or you're coming to a hill, and you want maybe not a very big one, and so you speed up so that you'll have enough momentum to get over the hill, so to speak. And we understand the concept. We understand that a bicycle has far less momentum than an automobile, which has far less momentum than a railroad train, and so on. So we have these obscure qualitative understandings of these words. The challenge in physics is that we quantify them, and we use them to calculate and use them to predict. Now, in the case of momentum, and to some extent with energy too, you have car accidents. And of course, in the case of a car accident, we have damage done, perhaps personal injury, and often we're trying to find out who was responsible. And was this person irresponsible in how they handled their vehicle? Was the vehicle not properly maintained? Was this person this or that? And based on the evidence of the scene, the amount of destruction, the way the car is damaged, the skid marks, and so forth, forensic investigators can put together very cleverly probably what happened, at least within reasonable constraints. And it's based on these ideas. And we'll come back to some of that later. But it's really important that we, and as soon as we finish the theoretical aspects of these units, we can then start getting into machines and the interesting stuff and the applications of how all these things help us every day. And I know this year is a very different kind of year, but we're going to try to at least do some of that, so hopefully get you thinking about some things that are a bit more interesting than just equations and problems in the textbook. So what we'll do now is we're only going to do a little bit of momentum, so I think I'll get it out of the way first. And when I'm finished with that, then we'll move back to energy and spend a great deal more time with it. So we have two basic types of momentum. I won't write them down because it doesn't really apply to grade 11. One is straight line motion. So we can say linear momentum, which we will cover this year. and this is lowercase p is a vector. We know there's going to be a vector because there's a force involved. At least it seems that way. And then the other one we have over here is rotational momentum, where we have spinning objects. And that's a case for advanced placement physics or in university, whichever it is that you see first. Now we said that we have force times time. However, the force need not be constant. So this leads us then to integration, where we get the integral of f dt. And furthermore, we can write m times a dt. The mass will be constant. So we have the acceleration integrated with respect to time, and that of course is simply mass times velocity. Put our vector hats on here. The unit of momentum, we have kilograms times meters per second. However, this is well, this is true. The common unit is the Newton second. And here we have a kilogram meter per second squared times seconds. And these two are of course equal. This is just easier to say. So we will describe momentum in terms of Newton seconds. Now there's some very interesting things about how momentum is perceived. Let's look at them for a moment here. Let's look at a change in momentum. With respect to time. So dp dt is equal to d dt of mv, which is simply equal to a force. And this is the true definition of a force. Okay, so the true definition is not F is equal to, and then based on our orientation system we use negative dp dt, not a push or a pull, which is, you know, kind of elementary and it's not very precise. So the force is the rate of change of momentum. Now you can see in all of this, this is just second law, because an object will maintain its momentum, its current velocity. The mass isn't going to change much, and of course it could, but we will leave those for other days. So F equals negative dp dt is just Newton's second law. An object will remain, actually we could say, or first law, whichever way you want to do it, remain at a constant momentum I'll remind you, mv, until acted upon by a force. The act of changing the momentum requires a force. Now this leads us then to a conservation theory of momentum. And this is a fundamental principle in physics. But we need to understand this a little bit better. In which he said that now we have to deal with systems of particles. And there's slightly different definitions here, so let's clear it up, at least from our standpoint. We have the term closed, and we have the term isolated. A closed system, there is no mass exchange with the external environment. And an isolated system has no energy exchange. Most systems will be both. So, a system, closed and isolated, and this can be by direct information, it can be by inference. But you will have to realize that this condition has been met. Then the energy in of the system will equal the energy out of the system. There's no energy exchange, no external force, and therefore the momentum is constant. So if we look at, say, a car accident, after there is, of course, people slamming the brakes on, so let's forget about that part. Two cars run into each other and there's no brake action. Then the only aspects that reflect this situation are the cars themselves. Their momentum, how they strike, how they themselves crumple, and so forth. And this can be controlled because you have a fixed amount of energy. You have the energy of both cars as they were coming towards the collision. We can go to sports like curling and football and so forth. And to the first approximation, well, all these objects to some extent have minor interactions with the external environment. The primary thing is that they come together and the interactions that they have when they do so are caused by the simple or predictable, so to speak, because these energies are equal whether they go in or they go out. And the challenge for the youngster learning this material is first to recognize that this condition has been met, and second, that if that is so, what is the definition of these two? Now, we're not going to do a great deal of momentum. We'll do a little bit this year, but you can see already how these ideas are giving us more information about concepts we've already learned. We've defined mathematically now what a force is. We can actually calculate it. When you look at graphs, so forth, of elevations, you can begin, with a little more knowledge, we can begin to see why water flows down the valleys. It's actually mathematically predictable. It's not just something, of course it flows down the valleys. We get that, but that's qualitative. And if we're going to predict things in a meaningful scientific way, we have to quantify them. So, let's look at what we would be expected to understand in this course with respect to momentum. Now, momentum is not covered normally in grade 11, but because you're in tops, you get the deluxe treatment. So we're going to do what we call 1D momentum, and with a resting target. So this is number line motion, back and forth, that's it. So therefore, the collision is head on. Now remember, again, a collision is simply not the tragedy on our highway. This is a impact of two particles. Okay, and this can be planned or accidental. And a particle is anything with mass. So this can be an electron, a proton, or an automobile. Makes no difference. So we're going to have a situation where we have mass 2 sitting quietly, mass 1 coming towards mass 2. Mass 1 is not necessarily equal to mass 2. We will know usually the initial speed of v1, and we seek the final speed of v1 and the final speed of v2. Now I'll give you equations for these in a minute, but I'd like to do first use Van Bemel's law of extremes again to help us understand whether we've made a goof or not as we figure things out. So let's consider that before we actually do the equations. As it applies to momentum. So we're going to choose, our big mass M, we'll say, is a locomotive, since I'm a boy and I like trains. And the small mass, we'll say, is a tennis ball. Now the objects are floating in space. So we have no surface friction. So case 1, the locomotive runs into the tennis ball. So the question is, what do we expect? Given, so using Van Bemel's law of extremes, so we're going to have big M. If a locomotive was to run into a tennis ball, we would expect it to simply keep going with no distinguishable change in velocity. What's tricky is the tennis ball. And you see this not only with locomotives and tennis balls, you see this in another way. If the tennis ball was sitting on the tracks and the locomotive runs into it, as we see with other debris, it's going to get sprung off the front. It's going to be sent flying. It will be bounced off the front of the locomotive. It will not just stick to the front of the locomotive. And I'll come back to this, but I'll say it now. A metaphor for this would be kicking a ball. Ball sitting still. You come towards the ball and you kick it with your foot. The ball compresses as your foot, given that it's attached to your body, can't go any further in its motion. The ball now is compressed and, like a spring, launches itself off of your foot with the same energy, more or less, that you gave it when you initially kicked it. And the ball goes some distance. And this is exactly the same as the tennis ball going off the front of the train. So the tennis ball will launch off the front of the train like a kicked ball. I understand that this is a little bit weird, so I'm going to draw pictures for you. And this is what makes, I like to think, as we begin to get into things, now we can start talking about applications. And you can say, well, why do, for example, when we kick a ball, why does that work? Well, here you are. This is exactly why it works. All right, so part one. The locomotive approaches the ball. Actually, I think what I'll do, just to make it a bit easier for you to see, I'm going to make the ball in red. So the locomotive makes just the first contact with the ball. Nothing much has happened. So this is at some V, and this one is at initially V equals 0. Now what happens, of course, is that almost instantaneously the locomotive is going to accelerate the ball, and the ball is going to flatten. Ball compresses. And then, so now we're going to say here that the ball speed is increasing. Okay, it's getting accelerated. The locomotive is otherwise just steaming along. So now we have a case where the ball is at V, but compressed. Locomotive just keeps on going, doesn't care. And finally, you have a locomotive. So let's imagine that you had a locomotive and you took the ball and you pressed it against the surface and held it there and then let it go. Okay, that's what's going to happen. It's exactly the same situation. And the ball travels away at some V, which is almost identical, given a little bit of friction, to the locomotive's velocity. So then, this is going to be V plus V. So the ball will be traveling at 2 times the locomotive. This is to an external frame of reference, okay, like the side of the track, not the locomotive itself. And so that is the one that's the hardest to understand, I suppose. But this is something to think about, and it's to say, and again, I'll just reiterate, this is identical. Physics to kicking a ball. Now let's go back and look at the converse, where the locomotive is effectively at rest and the ball is thrown at the locomotive. So now we have the case 2, the ball goes towards the locomotive. And what we expect, again using my law of extremes, is the locomotive doesn't care, does not move much, and that the small mass will bounce back. This is what we would expect. And this one's a little bit easier to understand because here's your large locomotive and the ball gets thrown towards the locomotive and will hit this thing and compress. And then the next thing you do, just like in the previous example, when you have a compressed ball against the surface, you're going to get it bounce, it's going to launch itself off and come back. So the equations that we come up with must agree with this. And it's at sometimes in your studies you're going to forget something. Now obviously I've spent some time on the law of extremes here, and this takes a little bit of time, but obviously in real life when you're thinking about this and are familiar with the idea, you can do this in a few seconds and catch right away that this can't be right. So let's have a look at these equations and see if we can sift through this. So we have an equation for the final speed of the thrown object, the ball or whatever, and a final speed of the, so this is the target here. Okay? Now, it's going to base itself on the initial speed in both cases, because that's the only one we have. We have no idea what's going to happen otherwise. So, what we're going to find here is that we will have the combined mass of the system underneath. And actually, let me use the masses that we used just so it's clear what we're doing here. It doesn't matter. Actually, you know what? I'll just, no, I better do it. Better leave it general. Okay. Now, let's think about it. Throwing the tennis ball, it's going to be coming back at us. We need a negative. Okay? And if it's the thrown object, we'll say that's M1. So just say our target is M2. Okay? So M1 is the thrown object, and so it's going to get bounced back. So what we want to make sure of here is that there's a situation where that happens. This is going to be M1 minus M2. Okay? In this case here, we have M1 plus M2, but here we have 2 times M1. Now let's just see if this works. Now these equations can be derived. It's a very difficult derivation, so we're not going to waste our time with it. But let's just go over this. Again, the pattern is not that difficult, but it just gives you a sense of what it looks like. So in the case of the law of extremes here, as I used it to derive this, or just remember it, the tennis ball is thrown. This is going to be some velocity v1 or whatever it is, or sorry, here. Okay, this is a very small mass. This is a very big mass. So this is basically going to be negative m2, because this is not going to matter. This is going to be 1,000,000 times bigger, and this is going to be basically going to be m2 because m1 doesn't matter. So what you end up with is -1 here. Okay, and you get your effect. Okay, so in case 2, so case 1 and case 2, let's see what we got here. So first we had the locomotive hitting the tennis ball, and so we have a big M1 minus practically nothing, a big M1 plus practically nothing is 1. So we end up with is that V1F equals V1I, and this is for the big M. If we're doing it the other way, now we have the tennis ball bouncing back. And as I said a minute ago, now you have little mass and a big mass. This will be going to be equal to negative V1I. Okay. Then down here, our V2, in the case of the first case where the locomotive hit the tennis ball now is going to be traveling faster. So once again, M1 is the locomotive, M2 doesn't really matter, and you end up with 2. And this is exactly what it should be. Equals 2 V1I. That's an agreement. And finally, in the case of the tennis ball hitting the locomotive, and the locomotive doesn't do very much, well, we have 2 times this very small number divided by this very big number. So V2F is equal to almost 0 V1I. But it is traveling this way. So you'll be able to do a couple of basic problems just to toy around with momentum, but that's as far as we're going to go with it this year. Obviously, we can have glancing collisions, we can have more than one dimension, and all the rest, and all that does is make these equations more involved, okay? But just to get a taste of these, a sense of an isolated closed system, and calculating some of these things is quite interesting. I'm going to leave you with one other interesting point. A couple of them, actually. If we have, let's say that's our collision point here, there's this one. And we have big M here and small m here. So the center of mass, actually I'm going to do this another way. Misspoke. Let's make the masses about the same size. Okay? So M1 is roughly M2. It doesn't have to be exact, but just so they're comparable. So here's M1, here is M2. And this one is moving. So here, roughly speaking, I'll do it up here, is the center of mass, okay? Because these are about the same, so we're going to have a balance point. As we move closer in, let's suppose to here, the center of mass is now here. After the collision, we end up with something like this, where this one is roughly moving, moving a little bit, this one's moving faster, and our center of mass is now here. And so what you find is that the velocity of the center of mass is going to be equal, and this is where we have to look at about half of this, okay, of the difference of the two masses. So it's a bit of a tricky calculation because it's related to the two masses themselves. So if you, for example, have a really big mass, and this is practically nothing, the center of mass, the system is effectively here and is moving with the large mass. And so if you think of it another way, you could have this distance and this distance. So it's pretty much, it gets a little complicated. I don't know if I want to go as far as with this, but the point, what I wanted to say was as you go through the collision point, the center of mass does not change. It doesn't change its velocity. Is unaffected by the collision. This surprises people, but if you use a physics simulator online and you do some simple thing like this, the center of mass will just keep on trucking. The graph will not show any bump or modification to its slope because of the collision, and it makes no difference what these masses are. And that surprises people, but that's because the center of mass is not acted upon by an external force. Therefore, its velocity is constant. And that's maybe the point I want to make here. Now the thing is, with all of this stuff, is that you can read the definitions, and you can tell me this. But then when we do the problem, we get confused because there's a difference between memorizing a concept and understanding the concept. That's really the topic here. Let's look at another point of where this can really help us. And it's been sort of alluded to already. When we have collisions, to study a collision, for example, this is a problem because they happen very, very fast. Contact times might be, say, 10 milliseconds. So this requires very expensive equipment. So he just got cut off there. So just briefly, momentum then really helps us because it allows us to determine these post-collision events without having to deal with this highly technical equipment in comparison. And this can be done after the event. So for example, analyzing car collisions, or looking later on at sporting events and saying what we could have, would have, should have done in certain situations. So there you are. That's a bit of an introduction to the concept of momentum in the linear way. And we'll do more of it next year, of course, but that'll do, I think, for grade 11. So let's go back to energy now, and let's look at one of the more important aspects that we deal with in mechanical physics, which is that of kinetic energy. This is the energy of motion. And it is clear faster objects have more energy, and massive objects have more energy. These two factors play into this quite nicely. And we said that work, the amount of energy exchanged is equal to the work. And the definition of work is, of course, W. And then the force can vary in the real world. So we're left with work equals the integral of F ds. Now this is a vector product, and we'll come back to that for a moment, but for here we're going to say that F is parallel to displacement, and in that case we can just multiply. So we're not going to trouble ourselves too much with that, but let's have a look here at what this means. So work then is equal to the integral, and we've got ma ds. Then we have m dv dt ds, and we can write m dv ds dt. That's not what I want to write. I was on the right track. M V, sorry, just a minute here. There we go. dv dt ds, here we go. This is m, and then we're going to put ds dt dv, that's more like it, which of course is the integral of mv dv. And with your knowledge, this of course is 1/2 mv squared. This is work, and this is also equal to kinetic energy. And so this equation that I made a mess of shows you so work then, as you expect it to be, would be equal to the difference or the change in kinetic energy. Potential energy is stored energy. And there are many types. And I'll put here, often an object has more than one. So you have to be careful when you're calculating. Okay? Now we have to look at what these are, and often potential energy is computed by the work of an external force. Work done by an external force. To bring an object from infinity to some r. So when we're dealing, let's say, with gravitation, this works fine because we have the force of gravity is equal to negative g_mm over r squared. But the external force is going to be the opposite sign. It's going to act against it, okay, in effect. And imagine if you had two positive charges and you want to bring them together, you're going to push against that force. So the external force is going to be g_mm over r squared. So then the work done by the external force is going to be the integral of g_M small m over r squared dr, which will give us negative gm over r. So the star here is, remember, it is the work done by an external force to, from infinity to some r. I didn't bother with the limits of integration here, but if you work it out, you will get this. So let's not bemoan the situation. We're not going to do too much of gravitational work. That we've done plenty next year in AP Physics C for those of you taking the course. But now let's look at what's going on near the Earth's surface, which we've talked about already being kind of an exception. We don't deal with the radius of the distance from Earth being an issue. So here we go. What about near Earth's surface? So we already know that we assume the force of gravity is equal to mg. Okay? And now what we're trying to do here is, what we're really interested in the case of gravity, is we're interested in how much work gravity does in a given situation. So while we call it gravitational potential energy, it is really, it is truly the work done by gravity. So work is equal to force times displacement, and we get mgh. Now, h is the vertical displacement, and g, of course, is taken as less than 0, always. Now let's look at these vector products for a moment. So force and displacement are both vectors. Energy, be it potential or otherwise, is a scalar. There are two vector products, and we'll come back to this. So it's a scalar slash dot product, where we have vector times vector gives us a scalar. Now the other one is the cross product, which produces a vector, which we'll leave for now. So let's look at this product here. In 1D, a scalar product so vector A parallel to vector B is equal to A times B. Vector A anti-parallel to B is equal to negative AB. That's all we have to do. So for 1D computations, we're fine. For 2D computations, it gets more interesting. So we have now A dot B is equal to AB cos theta times the angle between the two vectors. This is better computed as AX BX plus AY BY. Just using components. This is the way to do it. Now what this does, of course, allows for vectors acting in odd directions. We have already seen this when we do 2D force calculations. A force pushing at a certain angle has greater or less effect on a mass. And the same thing will happen as in the amount of work that can be done. Now this will come back in questions, and you can have a look at it as well, but it's actually fairly straightforward. So I wanted to get back now to some things that I think are more important than this. Two important questions. So the first one is, which force is doing the work? And number two, on which object? So it's really important when you solve force and work questions that you know this. You have to have a complete and non-ambiguous understanding of which force is you're dealing with and on which object it is acting. If you do not have this fundamental constraint, you do not have enough information to compute your technical definitions. If you can't solve it, at least you don't understand the question. That's fair, but at least you don't understand what you don't understand. So it's critically important that you can answer both of these questions. So please take a few moments. Remember, folks, when I discuss and teach these things, I do this with my own spin. Okay? You will not find this in a book. You will only find this working with me, and it gives you some ways to think about this to hopefully make things a little better for you. Let's look at something else that we need to understand. So, sign conventions. For work. So as I said before, one thing we can do is the dot product will produce these. So if you've taken, we're going to say components properly taken, you have to do that. Okay, and all the rest of it, then you will get a good answer. Number two 1d. I've already said if the vectors are parallel, then it's simply just AB. If the vectors are anti-parallel, negative AB. But that's mathematics. Let's look at this qualitatively. One, if the work is less than 0, then the energy is being stored. Now, 2, if the work is positive, energy is being released. Now, what's critical here is for you to understand that this is this last 2 lines here is sort of like Van Bemel's law of extremes, in the sense that you're cheating to know what is supposed to be happening. Now, when you go back and do your computations, you can see, okay, I made a mistake because my sign's wrong. It may have been in your components. Maybe you didn't do the angle properly. Maybe you took G to be positive. But somehow a mistake was made because these 2 principles are immutable. The danger here is to make sure that you understand what force we're talking about. Let's take a simple example of raising a textbook from the table up to some height. When you do this, there are 2 forces acting. There's the applied force by the person's hand pushing the book upward, and there's the force of gravity pulling the book down. If we look at the book being raised, the person is acting upward with her force, and the displacement is also upward, so that the person lifting the book is thus doing positive work. This seems reasonable based on number 2 here as well. We clearly see the book moving upward, and it does seem that motion is occurring, the work is being done, there is an exchange of energy here, and energy is thus being released. On the other hand, the gravity force is acting downward, but the displacement is upward. So if we combine those 2 in a linear way, we get negative mgh. And when that happens, we're storing energy in gravity. And that seems quite reasonable, because as soon as we let the book go, it falls back down again. And so we have 2 forces in that question. And so if you were to answer that, they say how much work is being done. First thing I say is, okay, well, I didn't put it, it's been rubbed out. Which force are we talking about? Because if we don't know what force it is, you get 2 completely different answers. They happen to have the same magnitude, but they have different meanings. And even though energy can be negative or positive, it doesn't mean that it's a vector. It means simply whether or not we're storing energy or releasing it. Just the same with money. Are you spending it or are you saving it? Very, very similar relationship. So I'd like to say a little more about this whole issue of work by gravity. So if you have a building like so, and it has some height, we'll just say h, like this, okay? And you're going to have a potential energy here due to gravity, we'll say 1, and you'll have 1 down here, EPG2. And what we're interested in is not EPG 1 or 2, but the difference in the potential gravity energy, which of course is the work due done by gravity. However, because gravitational potential energy, some of it, is converted to, let's say, motion when you drop something, we make an exception. So, let's say here, from the top of the building to the ground, we have work equals force of gravity times the displacement. And gravity does work. However, it's interchangeable with potential energy. So locally, we call mgh potential energy of gravity. When it is actually work. So we just have to know this. Now, we don't have to worry about this when we get away from the surface of the Earth. Because as soon as we get away from the surface of the Earth, then things take a different spin to them, pun intended. And the gravity, so astronomically, we have potential energy due to gravity equal to negative big G, big M, small m over R. So if we say on Earth's surface, so we would have equals minus 6.67 E minus 11 for the gravity constant times the mass of the Earth, 5.98 roughly, E plus 24, times, say, 100 kilogram mass, divided by radius of the Earth in this case, so 6.378 E 6 meters. Notice it's not squared. Now we pull out our calculator. I'm sure you can see, without doing any calculation at all, that we're going to have a very big number. Now we can take slightly different values here, but what you can see, of course, is 10 to the minus 11, 10 to the 24 is plus 15, and 2 more is plus 17, sorry, plus 13, pardon me, then plus 15, minus 6 gives us something around 10 to the 9. So we're looking at, literally gigajoules here, and this is the potential energy at the Earth's surface. Now the negative means that the work done by the external force was negative, in the sense that the displacement and the direction of the force were opposite. And so gravity did positive work, and the external force did negative work, bringing it in. To have this object leave the Earth, you effectively have to make this zero. Okay, now that's another story, but that's the challenge you have, is in the total energy. This is just the potential part. We have to add kinetic and so on. But it just shows you how big the numbers really are. When we do MGH, we're dealing only with the minuscule difference between the top of a building and the bottom of a building, which is, of course, what really matters to us when we're trying to figure things out. So we cut a corner, but instead of calling that work, which it technically is, we call it potential energy. As long as we know that. Now, in astronomical situations, this won't happen, because the work is going to be the difference in the two potential energies, and you're going to have to calculate them both because you no longer have G constant. Okay, so this is something we should write here. So for work done by gravity in astro, okay, G is not constant. Have to calculate the potential energy by gravity 1 and 2, and then subtract. So MGH only at Earth's surface. And it's an approximation. Okay, now hopefully that makes a bit of sense. Now, as I said to you before, energy is abstract. This is one time when you should do all of the conceptual questions in your textbook, preferably with a chum online or something like that, because this is a time where you really have to get your head around the concepts. You might be able to give me every definition and write it all out beautifully and still stare at the questions. It is very common. It can be very abstract for people. We move from very concrete things like motion, and we increasingly move into more abstract ideas. Now let's look at the potential energy that we say is equal to mgh. So what's going on here? Well, let's have a look. Well, we have m, which we understand. We have g, which is a vector. And we have h. This is a displacement vector. But, most importantly, it's a vertical displacement vector. And the sign is in the direction of motion. So if we're moving up, it's positive. If we're moving down, it's negative. G is negative 9.8, and this is always true. So I said to you when we started the course, we have to be true to these signs. If we start making everything positive and then try to figure out the direction afterwards, sure, you can do a few easy questions. But in no time at all, you're going to be in big trouble. And especially if you start writing code. So I think the rule has to be that we start this off and be very, very careful with it. Now, of course, this is analogous to EP is equal to the force of gravity times the displacement. It's simply just the Fs equation. All right, let's have a look here at what's going on then. So if we have EP equals mgh, but as vectors, we have mg dot h. However, the acceleration vector is either parallel or, sorry, anti-parallel or parallel to h, always. So we ignore the vector aspect because we don't need it. So it really is mg dot h with the signs properly indicated. We write it this way, but we must use correct signs. And if you do assignments with me, whether it's this year when things are weird, or hopefully next year when things are less weird, we're going to be looking for that. because we really don't want to pick up bad habits, making 9.8 positive all the time, and then just fudging it somehow later on. Like I said, with easy questions, you can do it. All right, now let's look at this again here. I mentioned it in my words earlier, but let's talk about it now. So we have a tabletop, and we have a book. Now let's move the book down a bit. So the book is here, and we have a hand, and the hand is raising the book up. So H, in this situation, and here, the book is falling. So here, raising the book. So in this case, the H vector is upwards. It is thus positive. Is greater than 0. The acceleration vector of gravity is less than 0 always. A lot of young people learning this stuff figure somehow the acceleration of gravity changes direction. Now you know better than that, but you get fooled in these questions, and you just can't. Okay, you have to know your technical work well enough that that cannot happen. Now here, the vector, the displacement vector is downward, and we have a -1 in this case. So here, GH is going to be, signs are opposite. We're going to have less than 0, and this, of course, MGH is equal to the work done by gravity. You've got to know what the force is, and this is the gravitational force. This is storing energy, as we said earlier. Okay? So this is critical that you have this understanding here, and recognizing that which force, this is the gravitational force. If on the other hand we have the work done by the hand, this is FA, H, let's say, okay, then this is going to be a positive times a positive, okay, and this is giving us a work greater than 0, and this is energy released, and this is by the hand, which is exactly what you expect it to be. I mean, this is not Harry Potter. This is real world stuff. It's supposed to work exactly the way that it says it is. Now here, when the book falls, we have gravity. The force of gravity is accelerating the book. Okay? And the force of gravity, of course, points down. And this is parallel to, in this example, the H vector. So the work done by gravity here is greater than 0 because energy is being released. So we do the calculations correctly, we will get the correct sign, be it negative or positive, and we get and we can use my rule about energy being stored or released as a check to see if somehow we goofed it. And if you goof these things, overwhelmingly, you'll goof it for 2 reasons. And the first one will be you screw up the signs. You don't give respect to the signs. And 2, you might choose the wrong force or somehow get otherwise confused in the technical definition of the question. But choosing the wrong sign or having the wrong force work on the object and so forth can get very confusing. So we want to be very careful about that. Let's look at another type of device that gives you an example that is less obtuse than gravity. Makes a bit more sense, perhaps. So this is springs. So we know the force of a spring is equal to negative kx. This is, of course, we've already seen it. This is called Hooke's law. And so now we say, okay, to compress the spring, an external force does work. And this work is positive, in that the displacement is parallel to the applied force. Okay? So if you have here a spring that's now compressed, like so, then the force, the applied force, acted inward to compress it, and the displacement, we'll use x in this case, is gone inward as well, and so therefore the work by the applied force is greater than 0, and that's what you expect. We have done work on the spring, but in the same situation, the spring force is opposing us at all points. So the spring force is anti-parallel to the displacement vector, either when we compress or stretch it. It makes no difference. And thus, the work done by the spring force when it's compressed is less than 0, and we are storing energy, which is exactly what you expect. When you cock a spring, you're storing energy, which you later boink, let it go, and the thing goes flying. Now, for completeness, let's look and see what this looks like. So once again, we have the spring force equal to negative kx. Opposing this is the applied force, and this is equal to negative Fs, which is thus equal to kx. It is acting in the opposite direction to the spring force. Now, if we want to, so now the work done to charge the spring, let's do this another way here. In this case, we can take the potential energy. Potential energy of the spring is equal to the integral. In this case, you do your work from some infinity to some arbitrary point, we'll just say x. However, this infinity is actually x equals 0, or the equilibrium point. Any other point, the spring has energy. This is the only point where, by observation, the spring force cannot do work. So we write it a little differently. It's equal to the integral from 0 to some x of kx dx. And you'll notice that, and I should maybe use, let's not confuse ourselves with our English here, our letters. So let's do k s ds. There we go. This gives us, of course, 1/2 kx squared. And that is, of course, the potential energy of a spring. So once again, this is positive. It's greater than 0 because if you let it go, the spring will bounce back. If we put something from gravity on the tabletop and let it go, it doesn't bounce back up again. So the potential energy here is positive, not negative. Okay, the amount of work done to cock the spring is positive work. The amount to bring a mass in from a distance with gravitation is negative work. So they're different, different ideas. Okay. I think I'm going to do work with the human body for a minute, and then we'll do some other things. This is misunderstood a great deal by people. Now let's just take a situation we call a bench press. And you can always look this up on the net. A very common exercise. So the athlete, here's the table, and the athlete is lying on the table pretty much flat, and there is a large, generally fairly heavy mass, like so, and with their arms they move this mass up and down. You always want to be careful doing this. Remember, if you use barbells and you do too much and you're too tired, the barbell will come to your chest and roll to your neck. That could be a very serious injury, so you want to be cautious about it. So it's better to use, if you do go to a gymnasium or have exercise equipment, you can still have the same effect, but the exercise equipment cannot fall on your chest. So be very careful about that if you decide to take on some kind of program. However, the point I wanted to raise here is this, is that when finished, we have a couple of things. One, the barbell is in its start position. And two, the athlete is sweating typically, if the weight was a reasonable amount, and tired. Okay, most of us would agree that we agree on those particular results. However, the misconception barbell net displacement equals 0. So work equals FDS equals 0. No work done. This gets used. Now you might want to be careful how you say that to a person who's strong enough to do bench presses, because there are certainly people who can do them at well over 300 pounds or more, and you might want to be careful how much you say things like that to them, because they certainly build their bodies. This is a very effective weight training thing. When you do a push-up, you are basically doing a poor man's bench press, because you're just simply inverting the situation, using your body as the bench press, as the barbell. So let's look at this. So what is the misconception here? Fine, it's easy to criticize and say that, you know, this isn't what should be, so what's going on? Well, here's the deal. The work done by gravity is 0. But that's the wrong question. Like I said earlier, we have to make sure we understand what's going on. We have to understand what force is doing the work on which object, and that's a mechanical situation. What happens in a bench press and many other exercise situations is the following. I'm just going to redraw things here with the human arm, just representative. So we have the hand here, and there's the elbow and the forearm, and we have our bicep and tricep muscles here, and they're connected to the joints with what we call tendons. Okay, and I guess I've got the elbow backwards. Let's fix that up before I get yelled at by somebody. There we go. And we'll put in a tendon here and a tendon here, and of course this is a vast simplification. So when muscles are actuated by the body, when a muscle flexes, it shortens. This is chemical work. By the body on itself. Now this is exactly why the definition of energy cannot just be the ability to do work, because This is a situation here where we are getting a shortening, but the cause of that shortening is a chemical reaction in the body itself. The nerve stimulates certain things, but the sugars and the other aspects in our blood cause this to shorten. And this is actually a very aggressive activity, as you'll see later when we do machines, but these muscles are much stronger than you actually sense them because they're working at a fairly significant mechanical disadvantage. So, an athlete then is doing work on themselves by flexing, especially against a significant external force. So work is done both raising the barbell but also lowering it carefully. Now we'll come back to some other aspects of the human body, but just to say it in English, so the athlete is sweating because their blood temperature has increased and the body is trying to cool itself. The blood temperature increases because of the effects of doing work on themselves. I've been told this is approximately, depending on who you speak to, somewhere around 55 to 60% efficient. The rest goes as heat. Now this is much better than, say, a car engine, but it's still a significant amount of heat. So when these reactions, these chemical reactions occur that cause the muscles to shorten, you get the effect, of course, and it's quite a significant effect, but you also get a fair amount of heat. Where does this go? It goes in the bloodstream. That's the only place it can go. And the blood carries it away. Naturally, our body has a fair amount of blood near the skin, and we lose a certain amount of heat as we're supposed to anyway. But if you do a substantial amount of work, the blood temperature raises to the point where the body has to enhance its cooling system. And we will talk about that. So it's a very interesting question because you can come up with some silly ideas about the person, an athlete, is not doing any work at all by raising barbells. Well, that's complete nonsense because if no other reason, the person's physique improves, their strength improves to become stronger. So clearly there's a change going on. There's an alteration of circumstance. So we have to always be mindful when we hear silly things sometimes, whether it's on the internet or what have you, or the explanation of a phenomena in your later studies. It doesn't ring true because of such simple situations as this. We need to think about those things when we study these things. Another story you're going to hear from some is about work on closed paths. Now we're going to do an example for you, but let's just talk about it at first. This is saying that the initial position is equal to the final position. That the shape of the path is not relevant. And we have two cases. where we have a variable force and remember with variable this can be magnitude and or direction. So one of the things that's really important as we work through these things in this course is to remember that a variable, or vector especially, is only constant if direction and magnitude remain the same. This is very clear, I think, if you think of it as an ordered pair. And of course the other case is a constant force. And here we have no variation in magnitude or direction. And so we're going to compute the work done and try to understand yet another misconception. I'm going to say it verbally first, but it will come to clear when we do the example. You will hear that a work around a closed path is 0. Move on to the next step. The work around a closed path is always 0. And that is only true, for sure, if the force is constant. If the force is variable, you might get the odd coincidence, but it almost always will not be 0. And this is where we have to be very careful about this. And so it's important to say work on closed path is 0 if the force is constant. And the reason, and this is another thing we talk about when we deal with students learning these new concepts. Most students in high school will not deal very often with variable forces, primarily because it requires the use of calculus. So they walk away being told that work around a closed path is always 0. And what happens, of course, is they get to university and it isn't. And professors love that kind of stuff. Now, I'm not saying we have to learn everything in the first year or the second year even, but I think we have to learn it correctly and recognizing where it goes. You can certainly tell a grade 11 student that this could happen. They may never have to make this calculation, but they should be able to be aware of it. Now, let's rub this off and let's look at an example that's not too difficult to compute. So let's suppose our path is going to be a rectangle. And we'll have 4 points on it here, okay? So this will be the origin. This will be 2 plus 2 comma 0. This is going to be plus 2 comma plus 2. Let's not bother with the pluses for this. These are just coordinates. I'm getting ahead of myself here. 2 comma 0, 2 comma 2, and 0 comma 2. All right? So we're going to have a force, this force blowing here, like so. And this we'll call force 1. Force 1 is constant. And we're going to say that force 1 is, so force 1 then will equal plus 2 comma negative 8 newtons. And we'll have force 2 will follow the path. So we're going to have for S1, which is, this is point 1, point 2, 3, and 4. So displacement 1 will be from 1 to 2. Displacement 2 will be from 2 to 3, etc. And so what we're going to do then is we'll say F12 is equal to, we'll keep the magnitude similar, it won't be exactly the same. Let's say plus 8 comma 0. F23 will equal 0 comma plus 8. F34 will equal negative 8, 0, and F41 will equal 0, negative 8. These are all newtons. Of course, we won't bother with the units just now. Now, how do I know that? Before we get into any kind of calculation. F2 will follow the path. And if the object is traveling, let's use yet another color. It's going to go this direction and then this direction, like so. Okay? Just go around the box once. And we start and stop at 0, 0. F's going to follow the path. So F12 has to act this direction because that's the path. And we could change the magnitude, but that would be too easy. F23 going this way now has to be a positive in the y. Going this way, a negative in the x, and finally a negative in the y. Alright, so let us then do some calculations here. I'm going to have to rub out the right side of this given the limited space I have. So we've got, I'm just going to remind myself so I don't forget, plus 2, negative 8. And I've got my other ones I think I'm okay with. Alright, so let's do the work by force 1. So work 1 is equal to, now we're going to do this in pieces just because we want to show something here. So we'll say the work 1 to 2 is going to be equal to, and we're going to have plus 2, negative 8, dotted with the displacement here, which is going to be plus 2, 0. And this is equaling 4 minus 0 equals 4. Work 2, 3 is equal to plus 2, negative 8 dot 0, plus 2. Here we have 0 minus 16, negative 16. Notice that the force does not change, but the displacement picks up as it goes around. 3, 4, plus 2, negative 8, dotted with negative 2, 0. So once again here we're going to have negative 4, which cancels this one out. 4, 1 is equal to plus 2, negative 8, dotted by 0, negative 2 equals 16. So the work done by force 1 is equal to 4 minus 16 minus 4 plus 16 equals 0. This is exactly what they will tell you. The work around a closed path is 0. Okay, now let's rub this out and consider what happens with my variable force. Here we have work 1, 2 is equal to plus 8, 0, dotted with plus 2, 0, which is equal to 16. Work 2, 3 is equal to 0, plus 8 dot 0, plus 2 is equal to 16. Work 3, 4 is equal to negative 8, 0 dot negative 2, 0 equals 16. Work 4, 1 is equal to 0, negative 8 dot 0, negative 2, which equals 16. Work 2 then is equal to 16 times 4, which is 64 joules. So it is important to realize that the work around a closed loop is truly a 0 only when you have a constant force. Otherwise, it'll depend. The force may not always follow. It might do something different. Okay? Now I'll use some words here. In AP Physics we'll see this. So if F is variable, we can compute the work done is equal to the integral. And we use a ring on it of F ds. And this ring says is that path is closed. Now, considering all the conceivable paths, you cannot be specific. But if you're doing math at this level, you should be able to handle that. So the issue then, they say, is well, when you set this up, and whatever equation we have for the displacement vector and so forth, you have to set up your limits of integration so that the path is closed. That's the rule. If you don't do that, then you haven't done your technical work correctly. And we won't be dealing with that in this course. We will do that next year. And this is why I chose a square path, so we could do the calculations in a very simple way. Next year we'll deal with actual functions that you can integrate. Not too difficult ones, but nevertheless. And this is known as a line integral. In your calculus, I understand that you've done arc length. And that, of course, is the beginning of this. And so what we do basically is we take the force at that location and dot it with that arc length and integrate over the arc length. And that gives you the line integral. And these are used extensively in this type of physics. And we'll see a fair bit of that next year. Okay, so the final concept I want to talk to you about in this little world of work, energy, and power, before we're done and we can get to some interesting things, is that of power. And this is actually more important than many people think it is. It seems like an adjunct. It seems like something at the end of the day. Now, first off, we have to remember that star, power, often in casual language, implies force. A powerful storm. And, or a powerful engine. Power has nothing to do with this. Power is something else. So we need to forget this in technical discourse. It's fine for poetry, okay, but it is not adequate for our work. We have to be careful. And you have been taught and reinforced for the best part of your 16, 17, 18, 19 years, whatever it is, these words. And now we use these words that are very similar in a totally different meaning. And you will not rationalize these on the test. You'll have learned this for a few weeks and you'll have 16 years of self-talk and you're not going to remember it. So you have to study. You have to study it and you have to be on top of it. Power is the rate of energy exchange. By then, we say power is equal to the change in energy over time. A joule per second is then therefore a watt. And we often have heard that unit on light bulbs and so forth. Well, there's a whole bunch of implications by this. It's easy to remember such a definition. That's not very difficult, actually. But let's look into it a little bit more detail here. So if power is equal to d E dt. Then let's suppose we have force times displacement, or even better still, let's do it this way. We'll say d dt of the integral of f ds. So the act of the differential will cancel this. And what we'll get is something like this. This will transform itself into force ds dt, which is equal to Fv. But force and velocity are vectors. So power, yet again, we have a dot product, F dot V. And you can, of course, do this in a differential way if you need to, but that's not the point in particular here. So maybe for this course we can dispense with this and just try it the easy way. We could say that power is equal to E over T, which is equal to force times displacement over T, which is equal to force times S over T, which is equal to force times velocity. As you wish. Also, work is analogous to energy, and mostly power is equal to work per unit time. This is the one that we will use mostly. And again, these are just calculation ideas. It's not a huge issue in particular. So let us look now at some consequences, because this is probably where it leads into a better sense. A process. Let's not use a process in general. We can, but let's look at machinery because it makes more sense to most of us. A machine with high power must transfer a lot of energy in a short time. That is a major design constraint. Probably more so than anything else. So we look at economy car, and we look at a truck. The economy car, of course, is producing minimal power. That's why it's an economy car. The truck, of course, is all about a major amount of force, because it's moving significant amounts of mass or other machinery. Okay? And we could spend an hour going through all the possibilities here. It's very, very important. But it's also true for the human body, too. Something you experience every day. Roughly. So the health physics people don't need to call me. We have about 100 watts to run our bodies. This is to run our innards. Depending on who you talk to, the brain is about 15 watts, which is sort of like what used to be the light in the refrigerator. Now with LEDs, that probably doesn't work anymore, but at least it was a fun story at the time. If you're a person of less mass, it'll be a bit smaller. If you're a bigger person, it'll be a little bit more, but again, this is irrelevant. we have about 100 watts of demand. So let's suppose you're in class, you finish up with the studies in your physics room, and you have to walk, say, a couple of 100 feet at student pace to the math room. You're not generally going to be panting out of breath when you get there. If you were, your friends would be worried about you. Okay, so you see, there's no, typically, we're talking about a healthy person, of course, or reasonably healthy person, no stress. You can do basic chores, up, down, up a few stairs, not too many, and walking at a reasonable pace, doing things, talking, and so forth, etc. Doing light housework, and not have any problem. However, and we all know it gets worse. Beyond this, let's say 300 plus, and this of course now bears tremendously on your fitness level. On fitness level. So as I remind a lot of the top students, chess is not a sport. So that means you have to get your heart rate up and so on. Just maybe a novel concept to some of you. But nevertheless, it's how this works. So exclamation mark. And this is of course in watts. So then what you'll start noticing is increased respiration. As we have an increased demand for oxygen, okay, in the muscles. Another thing that we'll also notice is perspiration. And this is also related to fitness. It also is related to the local climate, and especially humidity. But because, just as I said a few minutes ago, your body's doing more, so you're going to produce more oxygen, you're doing more chemical work, and roughly 40% of that work is heat, which heats the blood up, and it's going to cause us to perspire. And this is stress on our body. Now the human body, like many, is one that responds to stress. If you train, your body will become more effective at this. If you stop training, your body will become less so. Now you still retain a certain amount of fitness. People who have been athletic at one age and then let things go a little bit, perhaps when they got a job and had a family, they didn't have time anymore. As long as they're careful, they still are way better than never have been an athlete. And remember, if you will, that who you are is your brain. That's your personality, that's who you are, and the rest of your body is keeping your brain alive. Okay, that's what it's for. It can go get things, it can grab food, it can provide locomotion, and all the rest. And so as a consequence, the objective, I think, for all of us is to make some fitness a way of our lives. An hour a day, one way or the other, or 7 hours a week. I know it's difficult in this COVID thing, but in general terms, this will pass. And having this as part of your life, not just something that a child does. You will find that when you're 50 and 60, you can do things and enjoy your life in a way that perhaps other people can't who have not done so. You cannot remain fit just by eating properly. It helps, but it's not enough. You have a three-quarter triangle: sleep, fitness, or exercise rather, and your food, what you take into yourself. And it's really that straightforward. Now, I've had the privilege before I taught to spend a bit of time with some high-performance athletes. And just to give you an idea, many of us would have trouble maintaining 300 or 400 watts for very long. Unless we've been training, we really have trouble with that. There can be people who are very strong, who can provide a lot of force, but they can't do it for very long because their fitness level is just not there, their aerobic fitness level, the ability to transport oxygen. One of the measurements of athletic fitness is called the VO2 rating. And this is basically the volume of oxygen your body can transport to, and this is a function of your lungs, your circulatory system, and so forth. And most of us are sitting in the 20s and 30s and 40s. World-class athletes can be in the 70s or 80s or 90s even. That's a truly amazing thing. When I was involved with bicycle racing, I had athletes well over 1,000 watts for more than 2 or 3 minutes. Many people in middle age try to do that would end up probably with a health issue. It's truly amazing. It's basically like sprinting uphill. And so I've had athletes whose resting heart rates were under 40. Think about that, under 40. So they're when they were doing something, they would not show stress at these levels because this is nothing for them. Sometimes an athlete would train with one of their friends or family for an hour just so they could warm up. Now their friend or family is toast when that's finished. And then they would go train at their level because they have to. And just like you find in other fields, academics even, as well as other things, the exceptional athletes are light years ahead of everybody else. They're just incredible at their fitness level. And this isn't even the Olympic champions. These are the people you haven't heard of who didn't quite make the team. They were just truly amazing. And you see the same thing in academics too. You see the kid who's 16 is already in university, and somebody else who's 16 or somebody who's 24 or whatever has never even learned what the kid knows. And that's who we are. We're tall, we're short, we're this, we're that. But the exceptional performers, the difference can become really, really big between the different groups. And you have to find, of course, what you want to do. Now, there was one other thing I wanted to mention, and I'm trying to remember what it was now. As I said, I'm not an artist, so I'm going to try. This is the CN Tower representation. I was around when this was built, and it looks like this tall, slender tower, but what's amazing is that the center of mass is about here. If you have ever had that thing when you were a kid, that clown, you could punch it and it would sit back up because there was mass on the bottom of it, well, that's pretty much what the CN Tower is like. You wouldn't believe the amount of concrete and stuff that's below the ground. I remember when they were putting the foundations in, it's just truly staggering thing. So the tower is actually very stable because, of course, you have wind and other things hitting it up here. And it's not very far. My impression was it was something like 100 to 200 feet above the ground, and they can tell you, but it's quite low, center of mass. Now, the reason I bring the CN Tower is the following. We're going to do a thinking experiment. Person 1, person 2, and we're going to climb the stairs. Now, we're not going to get into the details, but let's just say it's 400 meters. And let's say the mass of the student involved is 50 kilograms. Okay? Now, here's the point. The work equals mgh. Actually, it's not going to equal that. It's going to be the negative of that because it's the work you do. Negative mgh. Okay? This is going to be equal to... now, let's just take g for 10 now. We'll just say g is approximately negative 10. All right? And we're going to climb the tower, and we have a negative here. Okay, so everything's positive. 4,000. So 200 kilojoules. And it's the same over here. Here, we're going to run up the stairs. And we'll be done. T equals, say, 1,200 seconds, 20 minutes. Here, one step every 60 seconds. Okay, so we're going to say, take the typical, we'll take 20 centimeter steps. So we have 5, so we're gonna, there's going to be roughly 2,000 steps. It's a little bit more and less than that, but we'll just say 2,000 for simple math. 2,000 steps. So this is equal to 120,000 seconds, right? So that's approximately 1.5 days. And we'll let this person, we'll give them a nice chance to sleep, all this kind of stuff. We're not going to push them too hard, okay? Now, notice that the work is the same. This person is well rested. This person is exhausted. But let's look at the power. Here we have 200,000 divided by 1,200 seconds. We get about 167 watts plus the body itself. Okay, just because you climb stairs doesn't mean your heart and all that stops. Over here, we're going to have, well, it's easy to figure it out now because the way we did this, that's 1,200 seconds. This is going to be 100 times longer. This one here, the power is 1.67 watts. It is not noticeable. Okay, plus the body, of course. So you can see here, without thinking about machinery and things that are technical, just the human experience. You can run up the CN Tower stairs and be toast, be exhausted, sweating, panting heavily, all the rest of it. Or you hardly would even notice that you did it if you're willing to wait long enough. And this is power as it actually works. And this is why power is a misunderstood concept, because it is such an important concept of how things operate, how thick the electrical conductors have to be, for example, how strong different devices have to be, and so forth and so on. All of these things play into it, and becomes a very interesting calculation. So that's the story I have for work, energy, and power. And you can consider the assignment. What I want you to do in Chapter 6 is we can do 3 questions from each section, and those can be star, non-star, or whatever, I don't care. And let's get them in before the long weekend. So, you know, the 15th or something like that. Now, your seminars, and I'll send an email, but just since some of you actually watch this, I'm going to have your seminars, we'll make them do, we're going to move it ahead a week. So instead of starting on the 19th, I'm going to say that I want them submitted to me. You send me the link by the 25th. The 25th of May. You have then a little bit over 2.5 weeks to go. So hopefully that's acceptable. All right, so after this, we're going to spend some time on the applications of all of these things that we've been talking about in the case. And what I propose to do with you first is simple machines. And we start looking at how the ideas of work, energy, power, forces, vectors, motion, and all the rest of it show up every day. Because if we don't understand how our world works, all these concepts are simply something in a textbook. Thank you for watching.